Hey College Algebra, what we're going to be doing in this lesson is section 3.5, and it's going to be about rational functions and how to graph those rational functions. So we're going to be going over things like, I'll be throwing words around like asymptotes. We'll be finding several different types of asymptotes and plotting those on the graph and graphing the rest of the function from there. So let's get started first of all with the reciprocal function, this f of x equals 1 over x, and also 1 over x squared. Before we get into what those two basic rational functions look like, let's look at what a rational function is. And this is what a rational function is. It is a function where you have a polynomial, that's what p of x represents, divided by another polynomial. And again, q of x represents the other polynomial, where q of x is not equal to 0. Okay? And that is what makes a rational function a rational function. Alright, so here are some examples of rational functions right here, written right here. And something about rational functions is since q of x equals 0, those values where q of x is equal to 0 is going to be excluded from the domain because those are points of discontinuity. Then the graphs are going to be often broke into parts and divided up where you find those points of discontinuity. And those points of discontinuity are often known as asymptotes. We'll be looking at more of those. Okay, so the simplest rational function with variable denominator is called the reciprocal function. It's known as this right here, 1 over x. And I'll show you some facts and statements about that in the next few slides. So here's what that reciprocal function looks like. Okay, here we have an asymptote at y or x equals 0 and y equals 0. So the x and y axis here are our asymptotes. Okay, and so the domain for this rational function is going to be from negative infinity, starting over here, to 0, and that's the point where it's discontinuous, is at 0, and then it picks back up after 0 and goes to infinity. So this is where we get the domain. And then the same thing goes for the range of this rational function, is we begin negative infinity, go to where y equals 0, so that's why we have 0 here. And then we pick it up back up to 0 and go on to infinity. So one thing about this function right here says f of x equals 1 over x decreases on the interval from negative infinity to 0 and 0 to infinity. You see how both of these pieces of the function, as we go read the graph from left to right, it is decreasing. And then this piece right here, it is also decreasing. Yes, it's many times these rational functions are constantly decreasing or constantly increasing, depending on the way the rational function is along the xy coordinate system there. Okay, we should know by looking at this graph that it's discontinuous at x equals 0. I already stated that. It has a vertical asymptote at that point. Also, the y-axis is a vertical asymptote and the x-axis is the horizontal asymptote. Okay, again, kind of repeating myself there. This function right here, it is an odd function and its graph is symmetric with respect to the origin. So if you remember back last chapter, we were looking at even and odd functions, and an odd function stated that it would be symmetric with respect to the origin. To be symmetric with respect to the origin, that is y equals x. So this graph right here it is symmetric, meaning that this line right here is the mirroring line. What you see on one side of the mirroring line, you see on the other. In this example, what I'm going to show you is the graph of some other function that is very similar to the function 1 over x. But this one, y equals 4 over x, is what we're looking at, and like I said, it's going to look very, very similar to the 1 over x, just slightly different. Okay, so for comparing it to the 1 over x, notice how where x is 1, your y is 1. Because if we plug in 1 for our x value right here, we're going to get 1 over 1, meaning our y value is 1. So we have this point here. Same goes with negative 1. That's why we have this point here. Where it kind of differs for this graph of this function and this function is are these values here. I'm going to plot them. So y is equal to 1 when your x value is equal to 4. Okay, so I'm going to plot that point there. So when you plug in 4 for your x, you get 4 over 4, which is 1. So y value 1, x value 4. Kind of the same thing goes with the other value for y when your x value is 1. When your x value is 1, plugging in x here for 1, with 1, your y value is going to be 4 also. So plot that up here. Now we're going to connect these two dots right here with a smooth curve. But first I'm going to figure out kind of where I'm going to graph this. Okay, right about here. So there is about what our graph of our function 4 over x looks like. Now I'm going to do the negative side of it. That there. That there. Now connect those dots with a smooth curve. And there. That's kind of the difference you're going to see between the reciprocal function of 1 over x and then any other number over x. Okay, so there you go. There is y equals 4 over x. Now, it also asks us to give the domain and range and the intervals over which the function is increasing or decreasing. Well, the domain and range of this function is the same as what the domain and range of 1 over x is. So domain, start with negative infinity, go to 0. That's where it's discontinuous, is at 0, because that's our vertical asymptote. And then this graph right here, we begin at 0 again and move on to infinity. So domain of this function is negative infinity to 0, union that with 0 to infinity, and we're done. And then the range, again, going from bottom up on your graph, you would see that starts negative infinity, goes up to this point, it's discontinuous at y equals 0, and then continues on up to infinity after 0. So that, again, same as the domain for this one. Okay, so there's domain and range. And then if we look at the function and try to find the intervals for which the function is increasing or decreasing, you would see that the whole domain, it is decreasing. This piece of it is decreasing if we read the graph from left to right, and so is this piece. It's decreasing from left to right. So you would state decreasing. On negative infinity to 0 and 0 to infinity. Now we're done. Okay, on example 2, I'm going to show you a way how you can compare this function here that we have to the basic function of y equals 1 over x. Okay, so we know what the graph of 1 over x looks like, but what if we subtract or add a value of k to our x? If you remember from the last chapter, that means we are making our graph shift horizontally if we add or subtract a value to our x. So if we subtract a number from x, in this case, that is going to shift our whole graph over how many ever k units you have. So for this one, it's going to shift even our vertical asymptote that we have along our y-axis. Instead of at x equals 0, it's going to be at x equals 3. So that's where our vertical asymptote is going to be now. And then the rest of the graph, how we're going to graph it is, I usually just say find 2 points to the left of your vertical asymptote, find 2 points and plot them to the right of your vertical asymptote, and draw your smooth curve through those points. So on this one, this graph also has a reflection because of this negative right here. So instead of our graph being here, here, and those 2 quadrants, they're going to be flipped around. They're going to be graphed here and here. So that's what I'm going to do next, is graph those. Now we're never going to cross the x-axis or that vertical, well, neither horizontal or vertical asymptote. We usually never cross them. Okay, so there is the graph of f of x equals negative 1 over x minus 3. Now to look at the rational function defined by f of x equals 1 over x squared, it also has the domain of this right here, negative infinity to 0 in union with a 0 to infinity, but it does not have the same range, and we'll see that in just a bit. So here are some details about this function. This is what it looks like. We will never have any negative y values because of our function right here is being squared. If you square a negative, it's going to be positive. Okay, so what happened to the graph is this portion kind of stayed the same, but instead of having negative values on this side, they're all positive. Okay, so this, for a portion of it, for this portion, our interval that is on this side is increasing from left to right, if you read it, from negative infinity to our vertical asymptote at 0. That interval is increasing. And then the rest is decreasing. So from 0 to infinity, it is decreasing. And we should know that at x equals 0, that's our vertical asymptote. That is our point in which it is discontinuous. And then the y-axis is the vertical asymptote, and the x-axis is still our horizontal asymptote. And this function is symmetric with the y-axis. meaning what you see on this side is reflected across the y-axis. And this means it's an even function. So the other function, 1 over x, that was odd. This one, even. So what we're going to do to graph this example right here is apply our horizontal and vertical shifts similar to what we did in the last example. What this means right here is we have a vertical shift. It's going to be moving our whole graph down 4 units because this is our function and it's being subtracted by 4, meaning this horizontal asymptote that we have right here, our x-axis, it's going to be shifted down 4 units. So right here is our horizontal asymptote. And then kind of similar thing right here, we have a horizontal shift because our x has a value that's being added or subtracted to it, and since it's -2, it's going to be shifted over to the right 2 units. So what is our vertical asymptote at the y-axis? It comes over here at x equals 2. The rest of the graph is going to look almost exactly like what we have here for the function that I have graphed here, which is the 1 over x squared function, because that's what we're comparing it to. It's going to look almost exactly like that. And you can plot real points on it, but for time purposes, I'm going to just sketch it in here and what it kind of looks like. Okay, so from either side of this graph, whenever this goes up, it's getting closer and closer to this vertical asymptote, but it never reaches it on this side or this side. It never touches that or crosses that line of x equals 2. Same goes with this horizontal asymptote. It will get closer and closer as your x values get smaller and smaller. In this case, it will get closer to the value of -4, but will never touch. On this side, same deal. As your x values get bigger and bigger, it never crosses that value of -4. It just keeps getting closer and closer to that asymptote. Okay, so there is our graph, our function graphed. And now the domain and range for this right here. So the domain for this one, well, looking at from left to right, you can see it begins -infinity and then goes to this asymptote. So asymptotes, whenever stating domain and ranges, are key to stating them correctly. So -infinity to this asymptote right here, which is 2. That is the first part. Then union that, begin back with 2 to infinity. Now the range, looking at all of our y values, start from the bottom up. Well, there is nothing below this point right here. So where we're going to say our range begins is at -4, but we're not going to include that value because that is our horizontal asymptote. So the way we're going to say we're not going to include that number is by using a parentheses rather than a bracket. Say -4, and then the rest of the graph goes upward instead of nowhere else. It doesn't go down at all. It goes up here, then it goes down on this part, but never goes below that point. So it goes to from -4 to infinity is our range. And then for the parts of the function that is increasing or decreasing, and this is just for the domain that is increasing or decreasing, looking at this portion of the domain, we can say that that portion is constantly increasing, and then the other portion of the domain, the 2 to infinity, that portion is constantly decreasing. So you can state that in a statement, say decreasing, or there we go, decreasing on 2 to infinity, and then increasing on -infinity to 2. And we're done with that one. Okay, so to tell you a little bit more about asymptotes, here is what an asymptote is. Well, for a vertical asymptote, like I said, as your x values on both sides, as they get bigger, as they get really big or as they get really small, your x value is getting closer to that value of A, or your asymptote, your vertical asymptote, but never reaches it. And that's why we call it the line at y or x equals A is our vertical asymptote. And then for our horizontal asymptote, we have our x values are getting really, really large or really, really small, but it's getting closer and closer to a value of y. This can be restated as y is getting closer to a value of b. And that line where y equals b is our horizontal asymptote. Okay, let's look at how you can find each of these types of asymptotes. So, looking at your function to determine how you find a vertical asymptote, well, a vertical asymptote is the discontinuities where the denominator is equal to 0. So you're going to find those spots where x makes your denominator equal to 0. So to do that, solve the equation. Set your denominator equal to 0 and solve for your x values. And those x values that you find are your vertical asymptotes. And we'll look at some examples here in a bit on how to do that. Here's how to determine horizontal asymptotes, and there's going to be 3 possibilities that we have to consider to find these horizontal asymptotes. In this case right here, what I have for you on A, if the numerator has lesser degree than the denominator, then there is a horizontal asymptote at y equals 0. Okay, so what I mean by numerator has lesser degree than denominator is this up here. If my value of n on my leading coefficient, my leading term, is that power is has a lesser degree than the denominator. So if this is, say, this is 2 and this is 3, then that's lesser degree, and your horizontal asymptote is always going to be at y equals 0. Okay. Now same here. If similarly here, if your numerator and denominator have the same degree, your m is equal to your n, then you have a horizontal asymptote at this equation right here. What you do is you take your 2 leading coefficients on both your numerator and denominator and do this equation right here. Y is equal to your coefficient on your numerator over the coefficient on your denominator. And that's how you find the horizontal asymptote for when your numerator and denominator have the same degree. The last case of horizontal asymptotes I don't include because there is no horizontal asymptote for the last case. And the last case to consider is when the degree in the numerator is much greater than the degree in the denominator. So when those degrees, when n, let's see, I'll write that out. When n is greater than m, there is no horizontal asymptote. The only two types of horizontal asymptotes are the two I previously stated. But another type of asymptote that I know y'all have never studied before is something called the slanted asymptote or the oblique asymptote. And that is when the numerator is exactly 1 degree more than the denominator. And the oblique or slanted asymptote comes from dividing the two polynomials into each other. And the resulting line that you get as your answer without the remainder is where your slant asymptote is. And I'll show you an example of that. Before we move on to our examples, I have a little note here that's very important. It says the graph of rational functions may have more than one vertical asymptote. There can be many vertical asymptotes. Or it may have none at all. And then the graph cannot intersect any vertical asymptotes. That's going to be the case for any of your rational functions. So don't mistakenly cross over a vertical asymptote because it will never cross a vertical asymptote. And then also, there can be at most one other non-vertical asymptote, meaning for a horizontal asymptote or a slant asymptote, there's going to be either one or the other, and you're only going to have one of those things. You're going to have one slant asymptote or one horizontal asymptote, but you can have multiple vertical asymptotes. Alright, so before we move on to finding vertical and horizontal asymptotes and slant asymptotes, here are some steps for graphing rational functions because we're about to graph those also. You may want to start out by finding the x and y intercepts, but you definitely want to start out by finding all asymptotes before moving on to trying to graph this sometimes monstrosity of a rational function. Then steps 3 and 4 you can do these two things, but I often like to do this for the last two steps. After you find your vertical and horizontal asymptotes, say that this is where you have found your horizontal and vertical asymptotes to be. So you have one here down in the negative values. Then say you have a couple of vertical asymptotes, like this. Okay, so to figure out where your function is going to be graphed amongst all these asymptotes, I find two values that are to the left of my vertical asymptote, and then find two values somewhere here in the middle, and then two values that are to the left of your other vertical asymptote. So find a couple of values in each section that it's broken up into according to your vertical asymptotes. And then draw a smooth curve. Use your graphing calculator to help you in this and how the graph looks the rest of the way after finding all the vertical and horizontal asymptotes and plotting those. So that's an easier way to do it, is use your graphing tool, especially to help you sketch graphs. Alright, so this example right here, we're asked to find all asymptotes of this function here given, and then we're going to actually graph it too. So let's go ahead and find the vertical and horizontal asymptotes. So let's start out by finding the vertical ones first. Vertical is always the same. You take your denominator, you set it equal to 0, and you solve for your x values. Those x values you find are your vertical asymptotes. So take this, I'm going to label this VA. Take your denominator, set that equal to 0, solve for x. First, I'm going to factor it, because this is easily factored. And now, if I set each of those factors equal to 0, I'm going to get x equals 3 and negative 2. So there are my vertical asymptotes. Now for determining horizontal asymptotes, look at your degrees of your function. The one in the numerator is considered to be 1, and the one in the denominator is 2. So that right there, we have our degree in our numerator is less than the degree in the denominator, which means we have a horizontal asymptote at y equals 0. So that's going to be the case for any time that your degree in your numerator is less than the degree in the denominator. It's horizontal asymptote, y equals 0. Okay, so let's plot this on a graph. Okay. Alright, so vertical asymptotes, let's plot those at 3. And negative 2. Okay, and then our horizontal asymptote is at y equals 0, which is the x-axis. And you don't necessarily have to draw a dotted line, but I'm going to highlight it a little bit on my graph here. Okay, so for the rest of this graph, what I'm going to tell you to do is find 2 points that are to the left of the first vertical asymptote. So find and plot 2 points that are to the left by plugging in values of x and finding the y value. So in here, in this original function, you're going to plug in, say, negative 3 and maybe negative 2.5, so you can get something along right in here. Plug in those 2 values, find the y values, plot them. Okay, so we're going to get this point maybe, and then this one. Okay, I'm going to draw a smooth curve with those points. Okay, now let's find a couple of other points that are in between these 2 asymptotes. So between negative 2 and 3, 2x values such as negative 1 and 2. So negative 1 is actually going to give us this point here, I believe. Yep. And then 2 actually is right here on the x-axis. So here we have a graph that looks kind of like that. And like I told you before, our graph can cross a horizontal asymptote, but it will never intersect the 2 vertical asymptotes or any vertical asymptotes. Now the rest of the graph. Find a couple points to the right of this, and what you'll find are points that match something similar to this. Okay, there is our graph of our function. The main thing I want you to know how to do is find these vertical and horizontal and possibly slant asymptotes and be able to plot those on a graph and just figure out where the rest of the graph lies after you find those asymptotes. For this next one, again, we're going to ask to find all asymptotes of this function, and then we're going to graph it, okay? So start out with vertical asymptotes by setting your denominator equal to 0. So set x plus 1 equal to 0. Solve for x, you get -1. So that is your vertical asymptote right there. And then your horizontal asymptote comes from this right here. Look at the degree of your numerator, which is understood to be 1, and the degree of your denominator, which again is understood to be 1. Both degrees are equal. So the equation for your horizontal asymptote is going to come from this right here. There's also understood 1 there. That is what your y is equal to. 4/1. Or you can just say 4. And there's your horizontal and your vertical asymptote. Now, let's graph these things. Alright, now plot your vertical and horizontal asymptote, the equations of those, with a dotted line like I've been doing. So at 4, we have a horizontal line there, and then at x equals -1, we have a vertical line there. Now plot the rest of it by finding points that are to the left and then to the right of that vertical asymptote. So in for your x value, or x values in this function, plug in things like -2 or -3, -4, anything like that. So if you plug in points on this side of the vertical asymptote, you will find that your graph is up here in this area. And then the rest of the graph, if you find points that are to the right of your vertical asymptote, it's going to be in this area right here that I'm circling right now. So it's going to look like that. Okay, so there is the graph of your function that I have for you here, and that is how you find those vertical and horizontal asymptotes. Okay, the last example I have for you is this here, and we're going to be looking at how to find slant asymptotes, because if we look at this, if you remember, the slant asymptotes will apply whenever our numerator here, the degree in our numerator, is 1 greater than our degree in our denominator, and that is this case here. So there's no horizontal asymptotes, but there is a slant asymptote for this one. Okay, but first let's find the vertical. So vertical asymptote, found always the same way. Take your denominator, set it equal to 0, solve for x. So vertical asymptote at x equals 1. Now your slant asymptote is going to come from dividing these two functions. Just like it says, x squared plus x divided by x minus 1. So divide these two functions, and your resulting function that you end up with after dividing is where your line is going to be, your slant asymptote. So we can label it slant asymptote SA or oblique asymptote, say OA. I like using SA. And then for this one right here, since we can use synthetic division to help us in doing this here, I'm going to say use the 0 at 1 and our coefficients 1, 1, and 0, because we have a plus 0, we don't have a constant. Let's do this now. 1, 1, 2, 2. So our remainder, our remainder is 2 here. But the remainder doesn't matter in this case. What we're looking for is this right here. That is our equation of our line that we're looking for. So a slant asymptote is at x plus 2. So on our graph, we're going to have the vertical asymptote at 1. Okay, let's do this. At 1, we're going to have that vertical asymptote. Okay, and then we're going to have a slant asymptote at this equation right here. At y equals x plus 2. So plot that line with a dotted line. X plus 2, b-intercept, or y-intercept right there. And it's going to go up 1 over 1. Okay. Okay, so we have slant asymptote of that equation there. And then how you find what the rest of your graph looks like is by figuring out where in the world the rest of the graph is by, again, focusing on the vertical asymptote. Where are your points found to the left of the vertical asymptote and to the right of the vertical asymptote? So plug in values like x equals 0, plug in 0 for all your x values, and plug in -1 for all your x values. That'll give you 2 points in this vicinity of the graph. And then do the same on this side of the graph. Plug in 1.5 and 2 and 3 and 4 to find points to the left and right. Okay, so what the rest of this graph is going to look like, it's going to be in between our slant asymptote and our vertical asymptote. It's going to look something like this here. Just like that. And there's the sketch of our function here with the slant asymptote. Alright, so that is all I have for you tonight, and I will hopefully see you all in class, and we will go over this some more. So goodbye, everybody.